In this video, I'll introduce the minimum spanning tree problem, define some terms that go along with that, look at an example why we might want to find a minimum spanning tree, and then we'll look at two algorithms, Kruskal's and Prim's algorithm that generates minimum spanning trees. I'll save the proof of these algorithms that these actually do generate minimum spanning trees for another video. So first off, what is a minimum spanning tree? Well, a graph, each of whose edges is assigned some real number, and each of these real numbers is called the cost or weight of the edge. So imagine a graph. Each edge I'm assigning a real number to it. We call that the cost or weight of the edge. And when we do that, we call the graph a weighted graph. So we've weighted the edges of the graph. We might also call it an edge-weighted graph if there might be confusion with a vertex-weighted graph. So that's what a weighted graph is. And then if we take a subgraph of a weighted graph, we can compute the weight of that subgraph and just define it to be the sum of the weights of its edges. So the minimum spanning tree problem is an answer to this question, or it's summarized in this question. So given a weighted graph G, what is the minimum weight of a spanning tree, and give me that spanning tree. This is the minimum spanning tree problem to produce such a minimum weight spanning tree. So for instance, I might have this graph G here, and I want to find a minimum spanning tree for this. So that is a spanning tree of G, but a special spanning tree, one that has the minimum weight over all spanning trees. Now, we should think about why one might want to, where this problem came from. And it has a lot of uses. So one way to think of a spanning tree is, right, it's a subgraph of a graph that is minimally connected, right? I put enough edges in there for the graph to still be connected, which is useful in applications. For example, if I have a road network or an electrical network, I want the whole thing to be connected, but maybe I don't want to use all of the edges. Maybe I'm trying to find the most efficient way to come up with a connected subgraph of this graph G. That's what a spanning tree is. And so we can think of this problem like a generalization of the problem of just finding a spanning tree, right? Finding a minimum connected subgraph of another graph. But in this case, we have weighted edges. So maybe these edges are, say, the time it takes to go from one vertex to another. So imagine this is a road network, something like that. Let's take that for instance. And then maybe these weights are the amount of time it takes to get from one location to the next by following the road network. So maybe each of these vertices represents a city, and an edge is a highway between the cities, and the weight is the length of time it takes to go between the two cities. Then finding a minimum weighted, minimum spanning tree here would be a minimum connected subgraph. So all the cities are connected in this subgraph, and we've been as efficient as possible with minimizing the distance, the sum of the distances between any two cities. That's one, for instance, of this problem. So let's look at a couple algorithms for determining a minimum spanning tree. So the first we'll encounter is Kruskal's algorithm. So for a connected weighted graph G of order n, we produce a spanning tree. We'll prove later that it's minimum. The structure as follows. So for the first edge, we just pick an edge and add it to the graph. And then any subsequent edge, we select one of minimum weight. Sorry, the first edge we should select also minimum weight. And then any subsequent edge, we add an edge of minimum weight unless that edge produces a cycle. If it does produce a cycle, we won't add it. If it doesn't produce a cycle, we will add it. So here's how that looks. So here I have my graph, my weighted graph G next to me, and over here I'm going to produce this spanning tree that hopefully has the minimum weight among all spanning trees. So what I'll do is I'll just first pick an edge of minimum weight. So I have a couple edges of weight 1 So I can choose either of these. Let's say U to Z. That one is weight 1. And then I'll continue on. Now I'll look at all the edges again. I'll look to add another edge. I'll select one of minimum weight. And so long as it doesn't produce a cycle, I'll add it. So XV is also weight 1. It doesn't produce a cycle, and so I'll add that to my tree. And now we continue along. So notice I have this weight 2 edge, and so I'll add that from U to W. That is weight 2. And let's see, so I've done the 1s and the 2s. Looks like I have 4, 5, 6, and 7 left, so I have this edge of weight 4. I will add that to the graph, WY. Why not? Let's add that one. And then let's see. I have this other edge, YZ, that's weight 4, but if I added it, that would produce a cycle, and so I can't add YZ. So my next minimum weight is 5. So I could do either YX or ZV. Neither of these will produce a cycle at the moment. So how about I add XY? That's weight 5. But now ZV, if I added that edge, it would produce a cycle, so I can't add it. And in fact, I'm done now because I've found a spanning tree of the graph. And so that's it. So here, the weight of this spanning tree would be 1 plus 1 plus 2 plus 4 plus 5. So that's what? Weight of T is, so weight of T equal to 13. And that's Kruskal's algorithm. So just select minimum weighted edges and add it to the graph if it doesn't produce a cycle. So this seems kind of like a greedy algorithm. So you might be surprised to learn that this always produces a minimum spanning tree. That is, this weight is in fact the minimum overall spanning trees. So let's take a look at another algorithm, sort of similar to that one. This one's called Prim's algorithm. So given a connected graph, here's how I'll construct the spanning tree. So again, I'll start now by just picking a special vertex. Let's maybe pick U as my special vertex. What I'll do is I'll select a minimum weight incident with U, a minimum weighted edge incident with U as my first edge. Okay, so I have 1, 2, and 6 coming off of U, so my minimum weight here is the 1 from U to Z. Now, for any subsequent edge, select an edge of minimum weight among those edges having exactly one of its vertices incident with an edge already selected. So that means I'm restricting myself now to U and Z. I'm only going to add edges that are incident with exactly one of those. So let's see. In terms of minimum weights, I have a 5 and a 4 coming off of Z. And off of U, I have a 2 and a 6. So the minimum of all those is 2. And so I'll add the edge UW, 2. And now I'll continue the process. Again, I'll only add an edge of minimum weight among those edges having exactly one of its vertices incident with an edge already selected. So let's see, another minimum weight. Coming off of U, I have a 6. Coming off of W, I have a 7 and a 4. Coming off of Z, I have a 4 and a 5. So it looks like the minimum weight among all of those is 4. And so I can add the edge YW. Well, let's add ZY. Okay, add YW in the other. Let's add ZY. That's fine as well. That had weight 4, and it was only incident with exactly one of the vertices. So continuing on, so I look at the edge YW again. Notice now this edge is incident with 2 of the edges that have already been selected. So I can't use YW anymore. So among all those edges, incident with exactly one edge that's already been selected, let's see, I have WX, it's 7. I have UV, that's a 6. I have YX, that's a 4. I have Z, V, that's a 5. I could add that one. It looks like 5 is my best option. That's incident with just one of its vertices is incident with one of the edges already selected. So let's add ZV. That had weight 5. And we'll continue on. Notice I have this edge XV here. That's now incident. So XV is adjacent to just one of the edges that we've already selected. And so I can pick XV that has weight 1. And now I'm done with the algorithm because I have produced the spanning tree. I can add up the weights. I get 13. So the weight of T is equal to 13, which is what we got the last time. It is a different, right? It's a different minimum spanning tree, but they both have the minimum weight. So it's slightly different than Kruskal's algorithm, but we'll still always, as long as we follow the algorithm exactly, always spit out a minimum spanning tree. Now, a note on just the complexity of these algorithms, which is the number of steps that the algorithm has to take, the number of computations that the algorithm has to do. These are both fairly good algorithms. These are on the order of n squared. Both of these algorithms are big O of n squared, meaning that they're bounded above by a quadratic polynomial of the order of the graph. And so this is pretty good. This is a polynomial time algorithm. Both of these are polynomial time. And so this problem of finding a minimum spanning tree just increases with the square of the order, which means that a computer can do even large graphs quite easily. What we try and avoid with an algorithm, if it's possible, is an exponential time algorithm. Anything that's polynomial is generally good for computers to use. So complexity of both of these is on the order of n squared. Increases with the square. The amount of time, the amount of data it takes to run the algorithm increases with the square of the number of vertices. Okay, that's it for this one. I'll see you next time.